Today we will continue with new chapter. This is electromagnetic waves, very important topic for our daily life, and it has many applications. First of all, I will talk about the importance of electromagnetic waves, and then we will discuss the plane electromagnetic waves and Maxwell equations, and we will describe the propagation of a sinusoidal electromagnetic wave, and we will describe the standing electromagnetic waves, and also we will discuss the amount of energy and momentum carried by an electromagnetic wave. The important thing here that we have three different electromagnetic waves. We will discuss this in that chapter: plane electromagnetic waves, sinusoidal electromagnetic waves, and standing electromagnetic waves. We will discuss these three types of electromagnetic waves. Today, I will try to finish that part and also that part. So let me continue with the importance of electromagnetic waves. Electromagnetic waves or light used everywhere in our life. So we use them in lamps, okay? So with different colors of light, we use them everywhere. And we use electromagnetic waves in our mobile phones. So you call somebody, you send message, or you receive messages and you receive calls. So how to do that? So there is no connection between your mobile phone and your friend's mobile phone. So you send electromagnetic waves and you receive electromagnetic waves. So this happens like this. For example, in addition to the normal communication procedure of the mobile phones, we have Bluetooth or wireless connection, okay? Both of them also use electromagnetic waves. So in communication, electromagnetic waves are very, very important. So just consider X-rays, for example. X-rays are also electromagnetic waves. You know the Röntgen machines, right? Röntgen machines use X-rays. X-rays are electromagnetic waves. So we use them in medicine to get the image of the body. And this is a computed tomography machine. These machines also use X-rays, so you can get the two-dimensional picture of the soft tissues. So very important devices in medical diagnosis. So in addition to that, there are radars. Okay, they use radio waves to detect the aircrafts and ships. So of course, they have some limitations. So there are long-range radars and short-range radars. So I will not go into detail. They use also electromagnetic waves. And what you see here, this is a very famous in these days. This is thermometer, but infrared thermometer. We use infrared waves, okay? So everybody emits infrareds, and without touching to the skin of the patient, you can check the temperature of the body by using infrared thermometer. In addition to that, you can use infrared cameras for night vision, okay? So these are also very important for military and civil applications. And what else? Here, what do you see? There is a rucksack, okay? So let's consider that you are entering into the shopping center, or you are entering into the airport, for example. They are checking your rucksack or bag. So by using X-rays in customs, also in the shopping centers, security people can see what you have within your luggage or within your bag. So this is showing the importance of electromagnetic waves for our life. So in addition to that, we have gamma rays. Gamma rays are also very important. We have UV light. We have also many applications by using the UV lights. So electromagnetic waves are very important for our daily life. And today we will learn how to produce electromagnetic waves, and what are the properties of the electromagnetic waves, and how to use them for practical applications. This chapter will tell us. Here, I show you electromagnetic spectrum. Maybe first of all, I should talk about electromagnetic wave. So why we use electromagnetic? Because the name comes from the property of the light. Here you see a sketch showing the electric field and magnetic field components of the light. Actually, light is formed from electric field and magnetic field in addition to that propagation vector. So each light has these three components. For this reason, light is also called as electromagnetic wave. Electromagnetic, okay? Another name is electromagnetic radiation. So what is electromagnetic spectrum? Electromagnetic spectrum defines us the different ranges of the electromagnetic radiation. Here we start from the radio waves. Here we have microwaves, infrared radiation, and here we have very short range, visible light range here. Here we have UV radiation, ultraviolet, and here we have X-rays, and here we have gamma rays. So this is the electromagnetic spectrum. What do you see here? From gamma rays to the radio waves, the wavelength is increasing, okay? Here we have wavelengths in meters, 10 meter, 1 meter, something like this. But if you go to X-rays and gamma rays, wavelength is decreasing. We are talking about 10 to minus 13 meter, okay? Compared to the radio waves, gamma rays have very small wavelengths. Opposite to the wavelength, frequency is increasing from radio waves to the gamma rays. What do you see here? That for the radio waves, we have frequency 10 to 8 hertz. And if you go to UV, the frequency increases up to 10 to 16, 10 to 17 hertz. And for the gamma rays, we have 10 to 22 hertz of frequency. So here I show you the relation between wavelength and frequency. This lambda is showing wavelength, and f is frequency, and c is the velocity of light in vacuum conditions. We will talk about this. So what do you see here? If you increase the wavelength, then frequency is decreasing. If you increase the wavelength, frequency is decreasing. Or if you increase the frequency, wavelength is decreasing. If you increase the frequency, wavelength is decreasing. We have another relation between wavelength and energy. This is the energy, this is Planck's constant, this is velocity of light, and this is the wavelength. If you increase the wavelength, energy goes down. If you decrease the wavelength, then energy increases. So look at that one. From radio waves to the gamma radiation or X-rays, we decrease the wavelength. Since the wavelength decreases, energy increases. So for X-rays and gamma rays, we have very energetic electromagnetic radiation. For this reason, we have different types of applications with X-rays and gamma rays because they have very huge energies compared to the radio waves and microwaves. So here we have very short region in electromagnetic spectrum. This is called as visible light. Human eye can see that region, and we cannot see these regions, okay? Here we have a range from red to the violet, and we have different colors: red, orange, yellow, green, blue, violet, and the colors in between. So a human eye can only see this range of electromagnetic spectrum. For this reason, this range of the spectrum is called as visible light. So let me show you example and you will better understand. Look at that one, radio waves. Radars are working in that range, and radio signals, FM, AM signals also working in that range, okay, between radio and microwave. And all communication, mobile phones, communications via satellites, okay, we use this range of the electromagnetic spectrum between microwaves and radio waves. So what we have here within microwave range, we have microwave oven. So we use microwaves to heat the food. And there are also many other applications in microwaves, but I'm just showing this one. So let's come to the infrared. As I discussed this infrared thermometer, we have infrared detectors or night vision cameras, okay? So depending on the temperature of the objects, you can get the picture during night. And in visible region, we can see that colors in nature by eye, okay? So just to remind you that the white color contains all these colors in the visible region. So in the UV region, we have, for example, applications. You can use UV radiation to check the originality of the money, okay? And UV light is also used in many applications. I can also say that they can be used for UV lithography in order to produce integrated circuits. And in X-ray region, X-rays are very important electromagnetic waves. They have many applications. I just show you here medical applications, computed tomography. Computed tomography can also be used in industry to check the defects and cracks in the productions. And gamma rays in nuclear physics experiments, gamma rays are used, and but also in medicine, in order to destroy cancer cells, gamma rays are used. So this is the electromagnetic spectrum. Energy is increasing from radio waves to the gamma rays, and wavelength is decreasing from gamma rays to the radio waves. So we have also opposite relation between wavelengths and frequencies of the electromagnetic radiation. Do you have any question related to the electromagnetic spectrum? So then let me continue with the details of the visible light. Visible light is the segment of the electromagnetic spectrum that we can see. So we can only see that range. So it is important to remind you. So it starts from 400 nanometer and it goes to 700 nanometer, from violet to the red. And we can determine that this wavelength range gives us violet color, this wavelength range gives us blue color, and this one green, yellow, orange, and red. But we have also another term, monochromatic light. What is the meaning of monochromatic? Mono means in Turkish tek. Chromatic, chroma comes from color, renk, tek renkli ışık. It means that you have single wavelength, okay? We are just talking about 450 nanometer, for example, or just 590 nanometer. We have single wavelength. This is called as monochromatic light. So not only from the visible region, also from gamma rays, from X-rays, you can produce monochromatic light, and it is very important issue in optics, especially when we are doing experiments with X-rays. This monochromatic light is very important. But of course, I will not go into detail. Okay, so let me give you that example for bio application for UV vision of the insects and birds. So here we have two pictures, both of them belong to the same flower. The name of the flower is black-eyed Susans, in Turkish güneş şapkası, or Rudbeckia, I think Latin name, I'm not sure. We can see this flower like this by eye, okay? But insects, bees, and birds can see like this. Completely different from our vision. You see? So the right picture taken with an UV sensitive camera, okay? So it shows how these same flowers appear to the bees that pollinate them. So bees can see like this, but we can see like this. So this is the importance of the UV vision for some animals. It is also valid for infrared vision, okay, which we have discussed here. So we cannot see during night, but some animals can see during night by using the infrared vision. So this is another bio application. So do you have any question until that point? If not, let's continue with the nature of the light. Here you see a scientist, Scottish physicist, James Clerk Maxwell. He was the first person to truly understand the fundamental nature of the light. He deduced correctly that the light was an electromagnetic wave, and the light is propagating in vacuum condition with some certain speed. This was explained by James Clerk Maxwell. And today, by using the Maxwell's equations, we will try to understand the nature of the electromagnetic waves. So just to remind you, I put the Maxwell equations here. So we have discussed them in chapter 29, you remember. So we have actually, during that semester, we spent our time to understand this laws, Gauss law for electricity, Gauss law for magnetism, Faradays law, Amperes law. So we have discussed all these things, okay? These are called as Maxwell's equations. So today we will use them to explain and understand the nature of the light. So what do you see here? We have electricity, electric field, we have magnetism, okay? And magnetic field. And we have relation between light and electricity and magnetism. So let me remind you that time varying magnetic field can produce a source of electric field, okay? This was the Faraday's law. And Amperes law tells us that a time varying electric field can produce magnetic field. Of course, it also includes displacement current discovered and added by James Clerk Maxwell into the Amperes law. So time-varying magnetic fields and time-varying electric fields can produce electric fields and magnetic fields respectively. So this is the main mechanism of the production of electromagnetic wave or propagation of the electromagnetic wave. So we will go into detail. Let's consider that we have a point charge. We have discussed this one during the first lecture or second lecture of that semester. We have a point charge and it is at rest. We know that this point charge at rest produces a static electric field, but not magnetic field, right? For example, if you have positively charged particle here, then we have electric field lines from particle to the space. We have discussed this one, right? But we have no magnetic fields due to that charge at rest. Now, let's consider that this point charge is moving with some certain velocity, with constant velocity, okay? What about the movement of the charges? Movement of the charges means that there is a current. So if there is a current, it means that we have electric field. So within the electric field, charges are moving. So in addition to that, if you have moving charges, it means that you have current. If you have current, then you can talk about the magnetic fields. So we have discussed all these things during the previous lectures. So then I can summarize that discussion that a point charge moving with a constant velocity produces both electric and magnetic fields. Is it true? Good. Now let's talk about an accelerated point charge. Point charge at rest, point charge moving with constant velocity, and the last one, an accelerated point charge. So the velocity of the charge changes by time. So if we have an accelerated point charge, we can produce electromagnetic waves. Don't forget this one. In order to produce electromagnetic waves, in order to produce light, you need accelerated charges, okay? Don't forget this one. So every mobile phone emits signals. I mean, you send message and you take the messages, you call someone and you receive calls, right? So how to do that? We emit signals and we receive signals in the form of electromagnetic waves that are made by accelerating charges within the mobile phone. How to do that? How to accelerate charges within the mobile phone? Remember the last lecture, RLC circuits. Within the RLC circuits, you can get this type of behavior of the charges, or in LC circuits, you can get simple harmonic motion of the charges, okay? So in LRC circuits, we have different behavior. I mean, a damped oscillations we have, then you can produce electromagnetic waves by using such circuits. We have discussed the radio station and also radio, how to take the radio signals from the radio stations. We have discussed LRC circuits. So the mechanism, I mean, if I say in simple form, that the mechanism is more or less same. Here, I show you power lines. We distribute the electricity. We take them from the power station to the home, okay? So there is a AC current here. So current fluctuates like this, oscillates like this. So then we have very huge amount of charge is accelerating back and forth and generating electromagnetic waves. So around that wires of the power lines, we produce electromagnetic waves, okay? So how to detect them, how to understand this? These waves can produce a buzzing sound from your car radio when you drive near the lines. So you produce electromagnetic waves. So it is related to the accelerated charges produce electromagnetic waves. Okay, here we have accelerated charges produce electromagnetic waves and we use them in communication. And here we have accelerated charges and they produce electromagnetic waves. So don't forget this. Accelerated charges produce electromagnetic waves. So now let's continue with plain electromagnetic wave. Here we have a simple form of plain electromagnetic wave, and I will try to explain how this plain wave satisfy Maxwell's equations. Here you see x-axis, here we have y-axis, and here we have z-axis. And I choose that electric field is along the positive y direction and magnetic field is along the positive z direction, okay? And we have no electric field and magnetic field components along the x direction. So here I define a plane. This plane divides that space into two regions. In one region on the left side, we have electric fields and magnetic fields, but on the right side of that plane, electric field and magnetic field are zero. Okay, just consider like this. And just also consider that electric field and magnetic field are uniform. They are not changing by time. Okay, and they have 90 degrees in between. They are perpendicular to each other. So this boundary, that plane, moves in positive x direction with a constant speed of c, let's consider. So this plane and this electric field and magnetic fields are moving like this in positive x direction with constant speed c. This is just assumption. We start with that definition, okay? So now, if electric field and magnetic field are uniform and perpendicular to each other and perpendicular to the direction of the propagation, this is the direction of the propagation, this type of wave is called as plane wave, okay? Electric field and magnetic field are perpendicular to each other, and they are also perpendicular to the propagation direction. So now let's try to apply Maxwell's equations to that simple plane electromagnetic wave and check whether Maxwell's equations satisfy that condition. Do you have any question here within that part with the definition of that simple plane electromagnetic wave? So now let's try to analyze that system by using Maxwell's equations. So we have 4 equations of Maxwell, right? So apply Gauss law for electricity, Gauss law for magnetism, apply Faradays law and Amperes law for that condition. Let's start with the Gauss laws and the simple plane wave here. So we have Gauss law for electricity given like this. This is closed surface, and this is the electric field. This is the area. This is Q enclosed over epsilon 0. We have discussed all these things in previous chapters. I will not go into detail. And this is for Gauss law for magnetism. It is equal to 0 because there is no magnetic monopole. We have also discussed this one, which is given again by closed surface B times area. So now let's apply these laws to that condition. Here we have electric fields and magnetic fields on the left side and nothing on the right side. Just define a Gaussian surface like this, a rectangular box, okay? And electric fields enter into that box and leave that box like this. And then magnetic field enters that box from that side and leaves from that side. So then what about that equation and what about that equation? So this box encloses no electric charge. So Q enclosed here is 0, okay? So then result must be 0 here. If you solve this one, it should give us 0 because there is no Q enclosed. Then let's see whether it is correct or not. So what about the total flux, total electric flux through that box? Electric fields are entering and leaving the box. So then the total electric flux through the surface is 0. Through this Gaussian surface, total electric flux is 0, then this side of the equation is also 0. Since there is no charge within the Gaussian surface, Q enclosed is also 0. So this simple plane wave satisfies Gauss law for electricity. Okay, what about the Gauss law for magnetism? We have magnetic field like this in that direction. So the total magnetic flux through that Gaussian surface is also 0, because the same amount of the magnetic field enters and leaves from the Gaussian surface. Okay, so the total magnetic flux through the surface is 0. Then this simple plane wave also satisfies Gauss law for magnetism. What about electric field in that direction, in positive x direction? Let's consider that you have electric field in that direction. Within the box, let's consider we have electric field like this, but on the right side, we have no electric field because this planar wavefront is moving like this. At the beginning, we have electric field like this, and also consider that we have electric field parallel to x direction. So if you choose a Gaussian surface again for that second condition with electric field in that direction, we have electric field entering into the box, but on the right side, there is no electric field. So then this Gauss law for electricity will not be 0 on the left side. Okay, on the right side, again, charge is 0, but on the left side, you will have some certain number since the total electric flux will be different from 0 if we have an electric field component along the x direction. So then it will not be satisfied by the Maxwell's first equation. So then we can tell you that in order to satisfy Maxwell's first and second equations, the electric and magnetic fields must be perpendicular to the direction of the propagation. So you cannot have any component of electric and magnetic fields along the propagation direction in order to satisfy Maxwell's first and second equations. So these fields are also perpendicular to each other. Then the wave is called as transverse. What is the meaning of transverse? Enine. Okay, so this is the propagation direction, and we don't have any electric field or magnetic field along the propagation direction. We only have electric field components and magnetic field components perpendicular to the propagation direction in order to satisfy Maxwell's first and second equation. Is this part clear? If not, please let me know. Okay, then let me continue with the Faradays Law and Amperes Law. Okay, so this simple plane electromagnetic wave should be consistent with the laws of electromagnetism, with the Maxwell's equations. So we have checked Gauss laws for electricity and magnetism. Then we will check Faraday's law and Amperes law. Okay, third and fourth Maxwell's equations. So let's continue with the third law of Maxwell's equations. What we have here, this is the Faraday's law. You remember EDL. This is closed surface, but we have line integral. Don't forget, this was a surface integral, but this is line integral, which is equal to minus the change in the magnetic flux as a function of time. So we have done it. Now we will apply that law to that simple plane wave. So let's try to calculate this magnetic flux first of all, and calculate that side of the equation, and then we will calculate this side of the equation. So let's start with the magnetic flux. We choose a loop here, okay? This is the planar wavefront, and it is moving in that direction, in positive x direction. The wave front is moving like this. And here we choose an area with that violet color area. So this area is shown by a times dx, change in the x-axis. Dx is given by velocity of the wavefront times dt. Velocity of wavefront is defined as c, okay? Then c times dt, this gives us dx. Dx times a gives us the area of that surface, okay, here. So then the change in the flux, magnetic flux, this is the direction of the magnetic field, and the flux changes by time. So B times dA. B is constant, and dA is given by A times C times dt. So the change in the magnetic flux can be written like this. What we have here, d phi b over dt. Just take this dt here, then you can get that expression. Time derivative of magnetic flux is given by b times a times c. C is the velocity of the wavefront, and a is this one, b is the magnetic field. So we have calculated the right side of the equation. What about the left side of the equation? In order to calculate the left side of the equation, just look at from that side. Here I have magnified picture of that side. This is y-axis, x-axis, and this is z. This is x, this is y, and we are looking from the z direction, let's say, okay? So this is the direction of the magnetic field from page to us, and this is the electric field along the positive y direction, the direction of the electric field. And here we have certain area, okay, same area here. This has area dA, and here we have dx given by c times dt, okay, and here we have a, okay, same closed loop here and same area. So in order to calculate that one, I choose a closed loop like this. Here I have dl, 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 and dl, so counterclockwise. And what about the electric field here in that path between E and F? Electric field is 0, okay? Then the contribution to that integral will be 0 from that part, and from F to G, dl and electric field are perpendicular to each other. Then again, it will be 0. And here between H and E, dl and electric field are perpendicular to each other. Again, they will give 0 to that integral. Only here we have dl and electric field. They are antiparallel to each other. Then the magnitude of electric field, and dl is given by a, then minus e times a will give us that integral on the left side. We have calculated the right side of the equation, this one, put it there and put it there. Finally, I can get that expression. E is equal to c times b. C is the speed of light in vacuum, b is the magnetic field magnitude, and E is the electric field magnitude. And this is the electromagnetic wave in vacuum. This relation is very important. Don't forget this one. Do you have any question here? So we just applied Faraday's law to analyze the simple plane wave. And now we will apply Amperes law to check whether it satisfies Amperes law in a vacuum. So Amperes law in general given with that expression. In vacuum, there is no displacement current. This term is 0. Then Amperes law in vacuum will be given by that expression on the left side and that expression on the right side, mu0 times epsilon 0 times time derivative of electric flux. So in order to solve that equation, we have to calculate left side of the equation, and we also have to calculate right side of the equation. So we have electric flux. The change in the electric flux can be calculated by using that expression, E times dA, okay, like magnetic flux. We have done all the things in the previous chapters. Here I choose again a surface, okay, and closed loop here. We have area given with, again, violet color. This is the C times dt, dx, change in the change along the x-axis, okay? This is the velocity of the wavefront, this is dt, and here we have A again, okay? And this is the direction of the magnetic field, this is the direction of the electric field. So have to calculate electric flux within that surface, electric field in that direction. And what is the electric flux here? Electric flux is given by E times dA. dA is given by A times C times dt. And here we have electric field. If you take dt here, then you can calculate time derivative of electric flux. Now we have calculated this part of the equation. Now let's try to deal with the left part of the Amperes law. So if you look from the top, you will see like this. These points are the direction of the electric field. This is the x-axis, z-axis, and this is xz plane, this plane. We are looking from y, okay, from top, you can consider. And this is the direction of the B along the z direction. You see this blue color, direction of the magnetic field. And on the right side here, we don't have electric field, we don't have magnetic field. Here we have the area which we have defined. This is the A, this is C dt, and apply this line integral closed loop, BDL. So what do you see here? Between E and F, there is no magnetic field, then the contribution to that integral will be 0, okay? And here, between F and G and H and E, magnetic field and dl are perpendicular to each other, then there will be no contribution again to that integral. So only from that part of the line integral, from the closed loop, we will have contribution to that integral between G and H. This is the direction of the dl, this is the direction of the B, then we have B times A, okay? This is the line integral for that closed loop. Just take this BA, put on the left side of the Amperes law, and just take this one, put it there. Finally, we will have this relation B is equal to epsilon 0 times mu 0 times C times E. We know epsilon 0, electric constant, we have seen in previous chapters. This is magnetic constant, and this is speed of light, and this is electric field, magnitude of electric field, magnitude of magnetic field. So by using Faraday's law, we got that expression. By using Amperes law, we got that expression. So they must be same, they should give the same result, right? Amperes law gives this one, Faraday's law gives this one. Then they must be equal to each other, okay? So then I can say that this epsilon 0, mu 0 times C must be equal to 1 over C. Look at this one. If you take E within that equation alone, take this one here, 1 over epsilon 0 mu 0 times C, will be equal to C, or epsilon 0 mu 0 times C will be equal to 1 over C if these two equations are equal to each other. Okay, then from that expression we can take C. C is the speed of electromagnetic waves in vacuum, can be given with that expression, square root of epsilon 0 mu 0. If you calculate it, it is given by 3 times 10 to 8 meter per second. This is the speed of electromagnetic waves, speed of light in vacuum conditions. Don't forget, the speed of electromagnetic waves in matter, in medium, is different. We will discuss this one during the next lecture. So now let's try to focus on the properties of electromagnetic waves. So we have 4 main properties with different colors. Here I show you. The first one, the electric and magnetic fields are perpendicular to the direction of propagation of the wave and also to each other. So electric field and magnetic field are perpendicular to each other, and both of them are perpendicular to the propagation direction. Okay, don't forget this. And there is a definite ratio between the magnitudes of the electric and magnetic fields. So E is equal to C times B. This is valid always. Of course, for vacuum conditions. So then another important and unique feature of electromagnetic waves, they require no medium, okay? They can travel in vacuum conditions. But mechanical waves, which we have discussed in Physics 1, are completely different, okay? They require medium to propagate. In addition to that, electromagnetic waves travel in vacuum with a definite and unchanging speed. So we have constant speed in vacuum for the electromagnetic waves, and the numerical value of that speed is given by that expression. What about the direction of the propagation of an electromagnetic wave? You can determine by using right-hand rule, okay? So this is the direction of the electric field, this is the direction of the magnetic field, and the direction of the propagation is perpendicular, both of them, okay, like this. So this was the plane electromagnetic waves and how Maxwell's equations can explain this plane electromagnetic waves. So we have done it today. So, but what we have assumed that both electric field and magnetic field are uniform. They are not changing by time, okay? During the next lecture, we will see sinusoidal electromagnetic waves. In that type of electromagnetic waves, both electric field and magnetic field will change by time, okay? Their magnitudes and their directions will change as a function of time. So we will discuss all these things during the next lecture. So also on Thursday, during the next lecture, we will discuss the standing electromagnetic waves, which have applications in microwave ovens. And we will also discuss the power and energy carried by electromagnetic waves. Do you have any question with that part of my lecture? Any question? If not, I will close the session. So take care of yourself. Bye-bye. See you on Thursday. And start to study and to prepare yourself for the second midterm exam.